Stretched into nothing. You think getting pulled apart would be the worst part. It's not. The worst part is that you'd be conscious for it. Stretched thin enough to see your own feet receding into a line below you, 1 atom wide. The tidal forces strong enough to tear you apart kick in thousands of kilometers before you reach anything called an event horizon. Take Cygnus X1, a stellar mass black hole about 21 solar masses sitting 7,200 light-years from Earth. Its event horizon is only about 18 miles across, but the killing starts long before you get there. Around a stellar mass black hole, the tidal force across the length of your body is about 9,000 newtons. That's roughly 2,000 pounds of force. Your diet, your workout routine, your bone density, none of it matters when the tidal gradient is pulling harder than your skeletal system was designed to handle, which, to be fair, was not designed for this. Think of a force strong enough to snap a steel cable, then 10 times that, enough to pull a car apart at the welds, then 9,000 newtons of tidal force, focused on the 6-foot length of your body, pulling your feet and head in opposite directions. Most people think spaghettification happens at the event horizon. For a stellar mass black hole, you'd be torn apart hundreds or thousands of kilometers before you got there. The horizon is just where the corpse stops being visible. A stellar mass black hole doesn't wait for you to arrive. It starts killing you from 6,000 kilometers away, which is roughly the distance from New York to Tokyo, except the commute is vertical and one-way. The wall of light. Every photon that will ever enter this black hole, from now until the heat death of the universe, is already waiting for you at one specific depth inside. A charged black hole, described by the Reissner-Nordstrom solution, has something no other type does: 2 event horizons, an outer one and an inner one called the Cauchy horizon. You cross the outer horizon and survive, but as you fall deeper, something impossible starts happening. Light from the outside universe begins piling up. Every photon that falls in after you gets blue shifted, compressed to higher and higher energy. A charged black hole is the universe's most elaborate bug. 2 event horizons, an inner firewall of infinite light, and the physics community still arguing about whether any of it matters because real black holes probably aren't charged anyway. At the Cauchy horizon, all of that accumulated light arrives at once. Imagine the light from a flashlight, then the light from a star, then every photon from every star that will ever shine, blue shifted to infinite energy, hitting you in a single instant at the Cauchy horizon. Physicists call this mass inflation, and it's not a metaphor. The energy density at that boundary diverges toward infinity. The theoretical math says the Cauchy horizon becomes a wall of radiation so intense that nothing, not matter, not information, not you, survives the crossing. The universe doesn't build its traps the same way twice. Every black hole is a different answer to the same question. What happens when gravity wins? You'd be killed by light that hasn't been emitted yet. The charged black hole doesn't just trap you in space, it traps you in everyone else's future. The gentlest death. What if the most terrifying moment of your life happened and you didn't even notice? What if you were already dead and the universe just hadn't told you yet? You could fall into a supermassive black hole and check your watch, stretch your arms, look around, and nothing would seem wrong for about 20 seconds. The point of no return for this one is the event horizon itself, and you don't even notice when you cross it. Take Sagittarius A star, the supermassive black hole at the center of our galaxy. 4 million solar masses. Its event horizon is 12 million kilometers across, 80 times the distance from Earth to the Moon. M87's black hole is even bigger, 6.5 billion solar masses, with a shadow 38 billion kilometers wide, bigger than the orbit of Pluto. And the tidal force at that horizon? Less than what you feel standing up from a chair. M87's black hole has a shadow bigger than our solar system. If it replaced the Sun, the event horizon would swallow Mercury, Venus, Earth, Mars, Jupiter, Saturn, and still have room for a parking lot. The event horizon is not a physical surface, wall, or barrier. It's a mathematical boundary. Locally, space-time at the horizon of a supermassive black hole looks perfectly normal, indistinguishable from floating in empty space. You'd cross it and feel nothing. From outside, you'd appear frozen at the horizon, redshifting into invisibility forever. Inside Sagittarius A star, you'd have about 20 seconds of proper time. Inside M87 star, potentially hours. A supermassive black hole is the only object in the universe polite enough to let you die comfortably. 20 seconds of peace, and then the same ending as everyone else. The middle ground. There's a weight class of black hole that physicists spent decades arguing might not exist, and falling into one is the cosmic equivalent of a death that's neither quick nor painless. For decades, scientists could find black holes the size of stars and black holes the size of galaxies, but nothing in between, until a cluster of fast-moving stars betrayed what was hiding at the center. The intermediate mass black hole sits between about 100 and 100,000 solar masses. Omega Centauri confirmed at least 8,200 solar masses in July 2024, detected via 7 fast-moving stars. In 2025, LIGO caught GW 231123, roughly 100 plus 140 solar masses merging into a 225 solar mass remnant, the most massive detection ever. Imagine being the size category of black hole that the entire physics community spent 50 years pretending didn't exist. Intermediate mass black holes are the middle children of astrophysics. A stellar mass black hole has a horizon the size of a city, a supermassive, bigger than the solar system, and in between, a horizon that might be the size of Jupiter, big enough to cross alive, small enough to crush you before you can appreciate it. We still don't have definitive proof that intermediate mass black holes exist through direct observation. The evidence is strong but mostly indirect. They remain the hardest class to confirm. The intermediate mass black hole gives you just enough time to realize what's happening and not nearly enough time to do anything about it. Dragged into the spin. Every other black hole on this list kills you. This one, in theory, might let you through. The math says there's an exit. The physics says it's probably a lie. There's a region around a rotating black hole where space-time moves faster than light, and if you enter it, you're forced to spin with the black hole whether you want to or not. The Kerr solution describes what happens when a black hole rotates, which is most of them. Gravity Probe B confirmed frame dragging around Earth at 37 milliarcseconds per year, space-time itself rotating. Earth's frame dragging effect, barely measurable. A neutron star's dragging nearby orbits by degrees. A maximally rotating black hole, dragging space-time itself faster than light can move through it. The ergosphere is the only place in the universe where standing still is literally impossible. Space-time is moving and you're moving with it. It's like a cosmic conveyor belt, except the conveyor belt is reality. Inside, the singularity isn't a point. It's a ring, zero thickness, non-zero radius. The Kerr solution allows passage through the ring to another region of space-time, but adding any matter, including you, destabilizes the inner horizon and likely creates a singularity you can't avoid. And here's where the point of no return gets strange. For a rotating black hole, it might not exist at all. There's a theoretical exit, but that exit collapses the moment anything tries to use it. A rotating black hole is the only object that offers you a theoretical exit and then makes the hallway collapse the moment you try to walk through it. If you're enjoying learning about what space would actually do to you, I post videos like this regularly, and I'd really appreciate it if you hit subscribe. Thanks. The bullet smaller than an atom. Every other black hole on this list is something you fall into. This one is small enough to fall into you, and it wouldn't even slow down. There may be black holes drifting through space right now that are smaller than a single proton, but heavier than Mount Everest. A primordial black hole at mountain mass, roughly 10 to the 12th kilograms, would have a Schwarzschild radius smaller than a proton. It wouldn't pull you in, it would punch through you like a gravitational bullet. A grain of sand. Then the mass of a mountain compressed into it. Then compress that mountain into a point smaller than a proton, and give it the gravitational pull to bend light around its surface. The Large Hadron Collider was accused of potentially creating one of these. The answer was, even if it did, it would evaporate in a billionth of a billionth of a billionth of a second. So less dangerous than the cafeteria food. In 2024, researchers proposed that Hawking evaporation may break down after half decay, opening a new mass window for primordial black holes as dark matter candidates. If that's true, there could be trillions of these drifting invisibly through every galaxy. We keep reaching for the edge of what physics can describe, and every time, the universe has already put something worse on the other side. A primordial black hole wouldn't pull you in, stretch you out, or even slow down to introduce itself. It would punch a proton-width hole through your chest and keep going. The universe's smallest, fastest, most indifferent killer. Torn apart by waves. Two black holes spiraling into each other is the single most energetic event the universe can produce. And if you're close enough, the space you're floating in starts oscillating, stretching you tall, squeezing you flat, hundreds of times per second. In January 2025, LIGO measured the clearest gravitational wave signal ever recorded. Detector arms changed length by about 1/1000th of a proton's diameter. GW150914, the first detection in September 2015. 36 plus 29 solar masses merged into 62, radiating roughly 3 solar masses of pure energy as gravitational waves. Over 300 total detections since then, 200 plus in the 4th observing run alone. A ripple in a pond, barely visible, spreading outward. Then a wave in the ocean, meters tall, enough to capsize a ship. Then a ripple in space-time itself, oscillating your body taller and shorter at 250 Hz, with enough energy to equal the output of every star in the observable universe combined for a fraction of a second. LIGO spent $2 billion to measure something smaller than a proton, and then it worked, repeatedly, over 300 times. At this point, gravitational waves are less revolutionary discovery and more Tuesday. Gravitational waves aren't destructive at distance. At the range LIGO detects them, hundreds of millions of light years away, they stretch the detector by less than 1/1000th of a proton. They pass through Earth constantly with zero biological effect. A binary merger doesn't spaghettify you or freeze you at a horizon. It plays your body like an accordion, stretching and squeezing until the atoms can't hold together anymore, and then it stops, because there's nothing left to squeeze. The most patient killer. Every black hole on this list is a trap. This one is a time bomb, and the universe set the fuse 13.8 billion years ago. In its final nanosecond, an evaporating black hole converts 228 metric tons of mass into pure energy, the most violent single-object explosion physics allows. Hawking radiation works like this. A solar mass black hole has a temperature of about 60 nanokelvins, virtually zero. It emits 10 to the negative 28th watts of radiation. Your phone's idle battery drain produces more energy. The most terrifying objects in the universe are currently being outradiated by screensavers. But as the black hole loses mass, its temperature rises, and rises, exponentially. A birthday candle, 1 watt of heat. A nuclear warhead, 10 to the 15th watts for a millisecond. An evaporating black hole's final second, 5 million megatons, 1,000 times every nuclear weapon humans have ever built, detonating from something that spent trillions of years barely glowing above absolute zero. A solar mass black hole takes 10 to the 67th years to evaporate. Black holes are not currently shrinking. They absorb far more energy from the cosmic microwave background than they emit. They won't begin net evaporating until the universe cools below their Hawking temperature, trillions of years from now. And that's the final point of no return, not a place. A moment in time. Wait long enough and the black hole comes for you. An evaporating black hole spends longer than the current age of the universe doing almost nothing. And then, in 1 nanosecond, it converts the mass of 228 metric tons into pure light, the most patient killer in the universe finally collecting what it's owed. If any of this made you rethink what black holes actually are, consider subscribing so you don't miss what's next. Thanks for watching.